finding the maximum and minimum values of a function of several variables. This is something that you learned how to do back in 167 for the single variable case. So first, let's quickly review that, and then I'll reveal what it is for multivariable cases. You can see how the two are actually quite similar. Find the max or min of a function of one variable on some interval a, b. How do you go about doing that? Critical numbers, some folks say critical points. Actually, Stewart's been known to use both terms. And that's where f prime of x is equal to 0. Okay, so that tells you where there might be a maximum minimum. Actually, it's not just where the derivative is 0. What else could be going on there? It doesn't exist. Like if there's a corner in the graph. But how can you tell if that point is a maximum or minimum, or maybe neither one? What do you do after that? Second derivative test. And there's a couple things you can do. You can also look at the first derivative and see sign changes, but for the purpose of generalizing to multivariable, we'll focus on the second derivative test. And what does the second derivative test say? That's what the second derivative tells you. But suppose you have a critical number, I'll call this x naught. So suppose you have a point where the derivative is 0, then you look at the second derivative. How do you use that to interpret whether this is a max or min or? Right. If it's positive, what?
If it's positive, is it a minimum?
Yes. Positive, it's a minimum. Negative, it's a maximum. If it's equal to 0, that is inconclusive. Right. And geometrically, what's going on here, as you might remember, say, so in this example, we have a maximum. So what's going up is finished going up, it's about to go down. Here it's been increasing where f prime is positive, decreasing where it's negative. So right here is where f prime equals 0. We have a horizontal tangent. And here the function is concave down, which means the second derivative is negative. So that's how we can tell that it's a max, not a min. So how does all of this generalize to the multivariable case? So for instance, so here's some surface, function of two variables, z equals f of x, y. And this function happens to have a maximum right here at x naught, y naught. So what's happening is, again, what's gone up is finished going up and must come down. So what we're seeing is a function is not changing in any direction. In other words, the gradient of f, what I'm going to say applies to any number of variables, not just two. So the gradient must be the 0 vector. So all partial derivatives at this point must be 0, or at least one partial derivative does not exist. So if that's what's going on, if all the partial derivatives are 0 or there's at least one that doesn't exist, then we have x naught is a critical point. In this case, we need to call it a critical point because it's no longer just one number, it's a vector quantity. So that carries over in a pretty straightforward fashion from the single variable case. So this is where you identify your candidates for a max or min. But then we need to do something that's analogous to the second derivative test for determining if we have a max or a min. The idea is this. It's called the second derivatives because, of course, you have several second partial derivatives, even in the two variable case. So what you do is you form what's called the Hessian matrix. So in the two variable case, you have the second partial with respect to x and x. In this entry, you have xy over here, fyx over here, and then fyy in the 2-2 position. Whereas in the three variable case, you'd have 9 second partial derivatives altogether. So the ones that have the same variable 3 times, those go on the diagonal, and then you have the mixed partial derivatives on the off diagonal. So what you can do is you can do, so the pattern that we have here, we have on the rows, fx in something, fy in something, fz in something. So across a row, the first letter is the same. Across a column, the second letter is the same, x, y, z. So that's how you can arrange them no matter how many variables you have. And you get an n by n matrix where n is the number of variables you have. So once you have the matrix of second partial derivatives, this is what you analyze to determine if it's a min or max or neither one. But because we're several variables, the picture gets a lot more complicated. So the test is this. If the Hessian matrix is what's called positive definite. So this is a generalization to matrices of the notion of a positive number. Then you have a min. I'll explain what it means for matrix to be positive definite in a minute and how you can easily test it for the 2-variable case, which is the one we're most interested in. If h is called negative definite, that's a max. If h is indefinite, then what you have is neither max or min. What you have is a saddle point. Saddle point means that the function is actually increasing along some directions and decreasing along others. Okay. So you end up having a graph that looks kind of like a saddle in some cases. So we'll draw what that is as we go. Finally, if h is singular, don't worry, I will define all of these, then inconclusive. This is a counterpart to the second derivative in a single variable case being 0. So these correspond to where an f double prime is positive negative. This has no counterpart in the single variable world. There's no such thing as, there's only one direction to look at. It's either increasing, decreasing, or neither. So now we need to see how we can concretely describe what all of these are in a way so that we can actually check these things. But I wanted to have in front of you that what's happening with the single variable and the multivariable case, that one does follow pretty directly from the other. We're just have to generalize certain things so they make sense when we have a matrix of partial derivatives rather than just a number. So when is a matrix positive definite? And we're going to assume throughout if it is symmetric, which is the case here. In other words, the entry in row I, column J is the same as the entry in row J, column I. So, for instance, fyx is equal to fxy, fzx is equal to fxz. How come, for the most part, we already know that's true? Yeah, the mixed partial derivatives, second partial derivatives, are equal whenever they're continuous. So this is something that we can generally count on, that this matrix is symmetric around the main diagonal. So these two are equal, these two are equal, these two are equal. These guys are equal. Okay. All right. So the definition of what it means for a matrix to be positive definite, if you take the matrix H, you multiply it by a vector x, and then you take the dot product of that with the same vector x, and x cannot be the 0 vector. And what you get is always a positive number. So that's how it's defined, and then we'll use that, certain consequences of it, to figure out how we can actually check in terms of these individual second derivatives whether it's positive definite. Now I'm going to mention a couple other properties of positive definite matrices. Now you might not be able to fully appreciate these unless you have some familiarity with linear algebra, like if you've already taken 326, which I don't know if these are actually discussed in 326. They should be. But some other facts that are good to know. All the diagonal entries are positive. So for instance, fxx, fyy are all positive. So if any of these are not, you know that it's not positive definite. So you can rule out a min right away in that case. But even if they are, it's not an if and only if kind of thing.